power consumption between a 12-volt system and a 120-volt system can be calculated. For the 12-volt system, the power consumption is 250 watts. For the 120-volt system, to determine the equivalent power consumption at 12 volts, the following calculations can be made. The equivalent resistance at 12 volts is equal to 120 volts squared divided by 250 watts, which equals 57.6 ohms. The current at 12 volts is equal to 12 volts divided by 57.6 ohms, which equals 0.21 amps. The power consumption at 12 volts is equal to 12 volts multiplied by 0.21 amps, which equals 2.52 watts. To find the power consumption difference, subtract 2.52 watts from 250 watts, which equals 247.48 watts. The 12-volt system consumes significantly less power than the 120-volt system, with a difference of approximately 247.48 watts. The on and off stress on light bulbs is lower in a 12-volt system compared to a 120-volt system due to the reduced voltage. When a light bulb is turned on, it experiences a high surge of current, which is known as inrush current. The inrush current is higher in 120-volt systems than in 12-volt systems because of the higher voltage. This higher inrush current can shorten the lifespan of light bulbs in 120-volt systems. A 12-volt MR16 bulb typically has a life expectancy of 3,500 to 5,000 hours. A 120-volt 50-watt halogen bulb typically has a life expectancy of 2,000 to 2,500 hours. In general, 12-volt MR16 bulbs have a longer lifespan than 120-volt 50-watt halogen bulbs due to the low voltage and reduced stress on the filament. When dealing with electrical systems and lighting, several key concepts and calculations are crucial for understanding their operation and efficiency. Firstly, understanding power, voltage, current, and resistance is fundamental. Power, measured in watts, represents the rate at which electrical energy is consumed or produced. Voltage, measured in volts, is the electrical potential difference that drives the current. Current, measured in amps, is the flow of electrical charge. Resistance, measured in ohms, opposes the flow of current. These quantities are related by Ohm's law, which states that voltage equals current times resistance, or volts equals amps times ohms. Secondly, calculating power consumption involves using the formula power equals voltage times current, or watts equals volts times amps. This formula allows you to determine the amount of power an electrical device uses when you know the voltage and current. Alternatively, you can calculate power using the formula power equals voltage squared divided by resistance, or watts equals volts squared divided by ohms, if you know the voltage and resistance. Thirdly, understanding the concept of inrush current is important, especially when dealing with lighting systems. Inrush current is the instantaneous high input current drawn by an electrical device when it is first turned on. It is often significantly higher than the device's steady-state current. This surge can stress the components of the device and the electrical system. Fourthly, when comparing different lighting systems, it is essential to consider their efficiency. Efficiency is the ratio of useful power output to total power input, often expressed as a percentage. Higher efficiency means that the system converts more of the input power into useful light and less into heat. Fifthly, bulb life expectancy is an important factor when evaluating lighting options. Different types of bulbs have different life expectancies, which are typically measured in hours. Factors that affect bulb life include voltage, current, operating temperature, and the frequency of switching the bulb on and off. Sixthly, when working with electrical systems, it is crucial to adhere to safety standards and regulations. These standards are designed to protect people and property from electrical hazards. They cover topics such as wiring methods, grounding, overcurrent protection, and equipment installation. Seventhly, voltage drop is a phenomenon that occurs when electrical current flows through a conductor, causing a decrease in voltage along the conductor's length. Excessive voltage drop can cause electrical equipment to malfunction or operate inefficiently. It is important to select conductors of appropriate size to minimize voltage drop. Eighthly, grounding is the process of connecting electrical equipment and systems to the earth. Grounding provides a path for fault current to flow back to the source, which helps to protect against electrical shock and fire hazards. Ninthly, overcurrent protection devices, such as circuit breakers and fuses, are designed to protect electrical circuits from excessive current. They interrupt the flow of current when it exceeds a safe level, preventing damage to equipment and reducing the risk of fire. Tenthly, when installing electrical systems, it is important to follow the manufacturer's instructions and local electrical codes. These codes provide detailed requirements for electrical installations covering topics such as wiring methods, grounding, overcurrent protection, and equipment installation. Let's expand on these concepts with more technical details. Regarding power consumption calculations, it is useful to understand how different types of loads affect the overall power consumption of a system. Firstly, resistive loads, such as incandescent light bulbs and heating elements, consume power directly proportional to the voltage squared. This means that if you double the voltage across a resistive load, the power consumption will increase by a factor of 4. Secondly, inductive loads, such as motors and transformers, consume power in a more complex manner. Inductive loads store energy in a magnetic field, which can cause the current to lag behind the voltage. This phase difference between voltage and current is described by the power factor. Thirdly, capacitive loads, such as capacitors and some electronic devices, also consume power in a complex manner. Capacitive loads store energy in an electric field, which can cause the current to lead the voltage. The power factor also applies to capacitive loads. Power factor correction is a technique used to improve the power factor of inductive and capacitive loads, which can reduce energy consumption and improve the efficiency of electrical systems. This is typically achieved by adding capacitors to the circuit to offset the effects of inductive loads, or by adding inductors to offset the effects of capacitive loads. Furthermore, when comparing the energy efficiency of different lighting technologies, it is important to consider their luminous efficacy, which is a measure of how much visible light a bulb produces per unit of power consumed. Luminous efficacy is typically measured in lumens per watt. Incandescent bulbs have a relatively low luminous efficacy, typically around 10 to 15 lumens per watt. Halogen bulbs have a slightly higher luminous efficacy, typically around 15 to 25 lumens per watt. Compact fluorescent lamps, or CFLs, have a much higher luminous efficacy, typically around 50 to 70 lumens per watt. Light-emitting diodes, or LEDs, have the highest luminous efficacy, typically around 80 to 100 lumens per watt or more. LED are also more durable and have a longer lifespan than other types of bulbs, making them a popular choice for energy-efficient lighting. When selecting lighting for a particular application, it is also important to consider the color temperature of the light. Color temperature is a measure of the warmth or coolness of the light, measured in Kelvin. Lower color temperatures, such as 2700 Kelvin, produce a warm, yellowish light, while higher color temperatures, such as 6500 Kelvin, produce a cool, bluish light. The appropriate color temperature depends on the application. Warm light is often preferred for residential settings, while cool light is often preferred for office and commercial settings. In addition to color temperature, it is also important to consider the color rendering index, or CRI, of the light. The CRI is a measure of how accurately the light renders colors compared to natural sunlight. A CRI of 100 indicates perfect color rendering, while a CRI of 0 indicates poor color rendering. For applications where accurate color rendering is important, such as retail displays and art galleries, it is important to select lighting with a high CRI. Let's delve deeper into the specifics of 12-volt and 120-volt lighting systems. Firstly, 12-volt lighting systems are often used in applications where safety is a concern, such as in swimming pools, spas, and landscape lighting. Because of the lower voltage, there is a reduced risk of electric shock. Secondly, 12-volt lighting systems typically require a transformer to step down the voltage from 120 volts to 12 volts. The transformer can be located remotely, which can further improve safety. Thirdly, 12-volt lighting systems often use low-voltage bulbs, such as MR16 halogen bulbs or LED bulbs. These bulbs are typically smaller and more compact than 120-volt bulbs, making them suitable for applications where space is limited. Fourthly, 120-volt lighting systems are the standard in most residential and commercial buildings. They are typically more efficient than 12-volt lighting systems because they do not require a transformer. Fifthly, 120-volt lighting systems offer a wider selection of bulb types and wattages than 12-volt lighting systems. This makes it easier to find the right bulb for a particular application. Sixthly, when installing 120-volt lighting systems, it is important to follow all applicable electrical codes and safety standards. This includes using the correct wiring methods, grounding the system properly, and providing overcurrent protection. Seventhly, the National Electrical Code, or NEC, provides detailed requirements for electrical installations, including lighting systems. The NEC is updated every 3 years, so it is important to stay up to date with the latest requirements. When designing and installing lighting systems, it is also important to consider the overall lighting design. This includes factors such as the amount of light needed, the distribution of light, and the control of light. The amount of light needed depends on the application. For example, a task area, such as a desk or workbench, requires more light than a general area, such as a hallway or lobby. The distribution of light refers to how the light is spread out in a space. Uniform lighting is often preferred for general areas, while directional lighting is often preferred for task areas. The control of light refers to the ability to adjust the amount of light in a space. This can be achieved using dimmers, switches, and occupancy sensors. Dimmers allow you to adjust the brightness of the light, which can save energy and improve the ambience of the space. Switches allow you to turn the light on and off, which can also save energy. Occupancy sensors automatically turn the light on when someone enters the space and off when they leave, which can further save energy. Let's further elaborate on the differences between halogen and LED lighting. Halogen bulbs are a type of incandescent bulb that contains a halogen gas, such as iodine or bromine. The halogen gas helps to regenerate the filament, which extends the life of the bulb. Halogen bulbs produce a bright white light that is similar to natural sunlight. They have a relatively high luminous efficacy compared to traditional incandescent bulbs, but they are less efficient than CFL and LED. Halogen bulbs also generate a significant amount of heat, which can be a safety concern in some applications. LED bulbs are solid-state lighting devices that use light-emitting diodes to produce light. LED are much more energy efficient than halogen bulbs and have a much longer lifespan. LED also generate very little heat, making them safer to use. LED bulbs are available in a wide range of colors and color temperatures, making them suitable for a variety of applications. They are also dimmable, which allows you to adjust the brightness of the light. When choosing between halogen and LED lighting, it is important to consider the following factors. Energy efficiency. LED are much more energy efficient than halogen bulbs, which can save you money on your electricity bill. Lifespan. LED have a much longer lifespan than halogen bulbs, which means you will not have to replace them as often. Heat generation. LED generate very little heat, which makes them safer to use than halogen bulbs. Color temperature. LED are available in a wide range of color temperatures, so you can choose the right color for your application. Cost. LED are typically more expensive than halogen bulbs, but the energy savings and longer lifespan can offset the higher cost over time. Let's also consider the impact of switching frequency on bulb life. The act of turning a light bulb on and off causes stress on the filament or other light-producing components. This stress is due to the thermal cycling, where the component heats up rapidly when turned on and cools down when turned off. The rapid heating and cooling can cause the material to expand and contract, which can lead to fatigue and eventual failure. The more frequently a bulb is switched on and off, the shorter its lifespan will be. This is particularly true for incandescent and halogen bulbs, which have a relatively fragile filament. CFL and LED are less susceptible to damage from switching frequency because they do not have a filament. However, frequent switching can still reduce their lifespan to some extent. To minimize the impact of switching frequency on bulb life, it is best to avoid turning lights on and off unnecessarily. If you are going to be out of a room for only a few minutes, it is often better to leave the light on than to turn it off and back on again. Occupancy sensors can also help to reduce switching frequency by automatically turning lights off when no one is in the room. Finally, let's consider the role of voltage regulation in lighting systems. Voltage regulation is the process of maintaining a stable voltage supply to the lighting system. Fluctuations in voltage can cause the brightness of the lights to vary, which can be annoying and can also shorten the lifespan of the bulbs. Poor voltage regulation can also damage the lighting system components. Voltage regulation is typically achieved using a voltage regulator, which is an electronic device that automatically adjusts the voltage to maintain a stable output. Voltage regulators are often used in lighting systems that are powered by generators or other sources that may have fluctuating voltage. In summary, understanding the principles of power consumption, voltage, current, resistance, inertia current, energy efficiency, bulb life expectancy, and voltage regulation is essential for designing and installing safe and efficient lighting systems. By considering these factors, you can create lighting systems that meet your needs while minimizing energy consumption and maximizing bulb life. The specific choice between 12-volt and 120-volt systems, as well as the choice of bulb type, should be based on a careful evaluation of the application requirements and the available resources. Always consult with a qualified electrician to ensure that your lighting system is installed safely and correctly.